Sounds good.
Start on time. All right, please welcome David Cook.
Hello everybody, I'm David Cook, and I did my honors research project on the effect of fly net corrosion on the hardness of Passageway N. So first off, a little background on electricity. We're going to start with this cool looking graph over here. The x-axis might be a little bit small for you to see, so it goes from, this is 1992 right here, this is 2017 right here. This is essentially just the world energy consumption. You can see that it rose relatively steadily all the way up until 2017, and it's expected to rise another 30% before 2030. You can see the gray, the red, and the green represent the three major fossil fuel sources of energy, and as you can see, they dominate the energy production market. With in 2012, they were 81% of the global energy production, with the other three main contributors being renewables, this little orange one, hydroelectricity in the blue, and the yellow is nuclear energy. However, in recent years, there's been worldwide initiatives such as the Paris Agreement, and while not every country has decided to continue going along with these initiatives, it does still represent where the world wants to go in the future in terms of energy production. In order to meet these goals, low carbon alternatives to fossil fuels would be required in order to reduce our carbon emissions. So we have these three other alternatives that could be used. Right now, renewables is, while promising with the current technology, they're both not efficient enough and they do not produce a steady enough source of electricity to be the sole alternative to fossil fuels and take a big chunk out of the world energy production. Hydroelectricity, it is more efficient than renewables, however it is very limited by location, and it does have a significant negative effect on the environment around it and the body of water where you were to place it. However, nuclear power doesn't have the restrictions of hydroelectricity in terms of affecting the environment or location, and it may also be the most efficient source of energy out of all of them, and it also can produce a very steady source of electricity. So a little bit about nuclear reactors. I have a very simplified diagram of a pressurized water reactor up here in the corner. So this is the reactor where the uranium fuel would transfer energy in the form of heat to a pressurized water coolant, and it runs through this loop, and then it transfers that energy to less pressurized loop of water, which is then vaporized, and the steam runs through the turbine, generating electricity. It also has this containment structure, which in real life basically does look like that, except it's huge and pretty much made out of concrete. That's because the pressurized water that runs through the reactor in the primary coolant loop, there's a potential hazard when you have water under high pressure. It's under that high pressure because this heat, obviously you can see here, if it was just let to run through without a high pressure, it would just vaporize and the pressure would build up, causing an explosion, which has happened before with kind of the more famous nuclear accidents that you've heard about. So every pressurized water is going to be required to have these huge containment structures, which is a significant cost and adds a lot of time to the whole construction process, which is why a lot of nuclear reactors, when they're being built, they go past budget and past the predicted deadline of being finished. Like I talked about in the last slide, in order to meet low carbon initiatives, we're going to have more nuclear reactors, and it's predicted that nuclear capacity will need to increase by 100% by 2050. And the current age of nuclear reactors right now is, average age around the world is 29.9 years. And obviously by the year 2050, if we're not building a lot of new reactors, it's going to keep going up, which means a lot of reactors will need to be replaced, which opens the door for new and exciting reactor designs that we have that are more safe, more efficient, and just kind of more advanced designs that are being thought out for a long time now. The Generation 4 reactors are currently not really in production, not really commercially viable yet, but by the year 2050, if more research is done, they might be able to. I chose to focus my research on the molten salt reactor because it's a very inherently safe design, as I'll talk about in the next slide. So this is a molten salt reactor. The main differences between this reactor and the pressurized water reactor that we saw on the last slide is this one uses thorium fuel as opposed to the uranium fuel of a pressurized water reactor. It's actually a lot more plentiful than uranium. It's more stable, easier to get in a form that you want to put in your reactor to generate heat safely. It produces less radioactive waste when it's run in the molten salt reactor, which increases the safety and the profitability of the system. And it's also able to produce more energy. It's more energy dense. And the other main difference that it gets its name from is the molten salt coolant. Molten salt coolant has a much lower vapor pressure than water, which essentially means that it can get to a much higher temperature before it vaporizes, which allows it to run through the reactor and the primary coolant loop while being at almost atmospheric pressure, which reduces the cost of running it through because you don't have to keep it so pressurized. And like I said, it makes it a very safe design because you don't have that pressurized fluid that could potentially cause accidents. It also has a high enough heat capacity to perform well in a reactor. It can get to much higher temperatures than something like water, like I said before. And it's, well, the main drawback of this design is that this molten salt is corrosive to basically any kind of metal surface that it comes into contact with, in the piping and the pumps, which is kind of where my research comes in. I'm trying to help remedy this issue so that this design could be commercially viable. And the molten salt that I chose to look into is FlyNac. It's a mixture of lithium fluoride, sodium fluoride, and potassium fluoride. It has a higher heat capacity than a lot of other molten salts. It has a low melting point compared to other salts and a lower viscosity, which decreases the power required to pump it through the coolant loop. It has a low vapor pressure, which we talked about before, makes it safer and makes it more efficient. And it is also less corrosive than a lot of other molten salts that have been studied that could be used in the reactor. However, it has a poor neutronic performance, which means that you wouldn't really be able to use it in the reactor in the primary coolant loop. So my study is focused on the secondary coolant loop. And the material I chose to look into was Hastelloy N. It's a nickel-based alloy with the weight percentages that you see on the side there. It has been found to be more corrosion resistant than other alloys. It's heat resistant. It could more than withstand the heat that would be present in the molten salt reactor. It's malleable, which makes it less expensive to use or to construct the reactor out of, as opposed to another metal that's harder and not as malleable. But it is also strong, and it could withstand the pressures that would be under in this reactor. So previous research that has been done using FlyNac and Hastelloy N are, one study looked at the corrosion mechanics between these two substances, and The main way that the corrosion happens is the fly net will actually draw the chromium and molybdenum that is in the Hastelloyenne to the surface, and then it'll eventually diffuse into the salt. Another study found that the fly net corrosion occurred mainly at the grain boundaries of the Hastelloyenne. And another study did a mass loss test and found that the Hastelloyenne was more resistant to fly net corrosion than other alloys that they tested it against. However, no study has been done to see how the fly net corrosion affects the mechanical properties of Hastelloyenne. Which brings me to my research question of how does fly net corrosion affect the hardness of Hastelloyenne? I chose hardness essentially because it was the easiest and simplest way for me to test the progression of the corrosion in the material. And it would seem to be it would get me the most accurate results in terms of how that corrosion is actually progressing. And there are also ways to associate it to a change in hardness to a change in yield strength or a change in ultimate strength, which is very important when looking into materials that would be used in nuclear reactors. So my methods for this, the first thing I had to do was melt the fly net salt mixture. And did this using essentially a charcoal foundry that I built with a shop vac for forced airflow to keep the heat consistent and high. And after this was melted and mixed, I placed 11 Hastelloyenne samples in that molten salt, and then I maintained the temperature to keep the salt liquid. And then I took the samples out one at a time at 5-hour intervals. So the last sample was taken out at 55 hours submerged in the molten salt. And after that, I took this cool picture of the melted salt. So then the testing for this, I tested the 11 samples that I just talked about that were exposed to the fly net. And then I also tested 3 control samples that had no exposure to the salt whatsoever. Tested them on a Rockwell hardness testing machine, which gave me data on the Rockwell B scale, which doesn't have any meaningful units in and of itself. It's mostly just used in comparing the hardness of materials to each other. So it suits the purposes of this project. And the hardness was tested at roughly the same 20 locations on each sample, so that you would get a good average hardness of each sample. And these are the results that I got from that. The first thing that you can see is this linear trend line. It has a distinctly negative slope, which means that the hardness, which indicates that the hardness did decrease over the 55-hour exposure time. And you can see, however, that the data is kind of scattered. So to kind of investigate more, I did do a statistical analysis, which is shown in the next slide. You can also see that the standard deviation over there, all the way on the right, is pretty high, especially when you consider that we're getting values around 80 on the Rockwell hardness scale. So those standard deviations kind of cause concern into how accurate the hardness readings are, because those standard deviations are based on the averages of each sample. One of the potential causes I looked into for this is some of the hardness values may have been taken at the grain boundaries of the samples. So obviously those would be a lot lower hardness values than you would get if it wasn't right on the grain boundary, which would increase the standard deviation, so you're getting a lot of different values. And like I talked about previously, the corrosion, at least in the short term, targets those grain boundaries, which might weaken them even more, increasing the standard deviation. average standard deviation we just talked about. This coefficient is what the model showed is how much the hardness is decreasing per hour. So it would mean that it indicates that the hardness decreases at 0.0993 per hour on the Rockwell hardness scale. The R-square value means that 34% of the variation in the hardness data that we saw was due to the amount of time that it was submerged in the finite salt, which obviously isn't ideal. You want to see 100% ideally, but it is significant. And the F value and the P value, long story short, essentially means that in a 90% confidence interval, this coefficient is statistically significant. So we can be 90% sure that the hardness of the Hastelloy N decreased at a rate of 0.0993 per hour on the Rockwell hardness scale. And this residual plot right here, I put that there to show how well the linear relationship fits with the data. You can see that it's a relatively random and equal distribution of residuals on either side of the line, which essentially means that the linear trend line is the correct fit for the data. So the significance of my study is the hardness was shown to decrease linearly at a rate of about 0.12% per hour, and this is a statistically significant linear relationship. And my study also showed a high standard deviation in the average hardness values, which, like I said before, could likely be down to hardness values being taken at the weakening grain boundaries. My findings also were found to agree with previous research, which did find noticeable corrosion after around the amount of time that I had in the Hastelloy N. And finally, there's additional research that is obviously required because of my high standard deviation and my short exposure time of 55 hours. When you think about how long a nuclear reactor is going to be, being used, it's a lot longer than 55 hours. So more experimentation should be done with longer exposure time to see how this corrosion progresses over time, because studies on other materials have shown that this corrosion rate does decrease a lot of the time. Is found to decrease in other materials. So longer exposure time and more samples so that you make sure you get an accurate result. Unfortunately, I didn't have the budget or the time to do this, but this would be a good way to get a more definitive conclusion on whether this parrot can be used in a molten salt reactor.